Right, this is the second of a 4-part lecture on the fundamentals of microbial metabolism for BIO367. Let's talk about energy coupling. We just talked about endergonic and exergonic reactions. Now let's consider ATP, adenosine triphosphate. And ATP hydrolysis is the reaction that is indicated here. Okay? ATP plus water react to form ADP, adenosine diphosphate, plus an inorganic phosphate group plus a proton. Okay, it's written out kind of in a longer form here. And let's look over here at the delta G value associated with this hydrolysis reaction. It's negative, so it's exergonic, and it's pretty large. It's negative 32. That's a pretty big value, actually. So you get quite a lot of energy from ATP hydrolysis. You also get a lot of energy from taking ATP and forming adenosine monophosphate, a pyrophosphate group in a protein, or taking adenosine monophosphate and hydrolyzing that to yield adenosine and phosphate. These are all, pretty high energy compounds. ATP hydrolysis, as shown here, is probably the most fundamental reaction in the cell, and it's what we're focusing on now. Very exergonic process. Well, so what, right? So it's very exergonic, which means it's a spontaneous reaction, and it's energy yielding. And what's really important about ATP is that ATP hydrolysis can be coupled or linked with cellular endergonic reactions to make them more favorable or to make them thermodynamically possible. So let's consider a theoretical reaction here. A plus B react to form C plus D. And let's say that this is a very endergonic reaction as written from left to right. So you would normally have to put energy into, not normally, you would always have to put energy into this reaction in order for it to occur. The way that we put energy into reactions in cells is most often to link them to ATP hydrolysis. So here we have another chemical reaction, ATP reacting to form ADP plus phosphate. That's ATP hydrolysis right there. It is exergonic. And it's got a delta G value of negative 32. Actually, it's negative 31.8, not to nitpick too much, but so we're linking the two here. So we typically in cells link ATP hydrolysis, which is shown here, to endergonic reactions that are happening in the cell. Okay? Let's think a little bit about what that means mathematically. Shown here is the synthesis of glutamine, which is an amino acid. A lot of microbes synthesize glutamine using glutamic acid and ammonia. Not all microbes, but a lot of microbes. So the blue box on the top is showing us that reaction, and it's showing us over here, it's a little fuzzy, but we've got a delta G, and it is positive. It's in units of kilocalories per mole, but let's not worry about the units for now, okay? So a positive thing, that means that this is a very endergonic reaction as written. Could not happen in the cell without the input of energy. The input of energy comes from coupling that reaction to ATP hydrolysis. So if we look down here, there's the reaction as shown above, and it's delta G associated with it. Here is the delta G for ATP hydrolysis when expressed in these units. That's why the number's a little bit different, and you'll notice that this is negative. Okay, so that's very exergonic. When you couple these reactions, you can then sum the total delta G value, and if you look here, you'll see that we have an overall negative delta G value. So by coupling the exergonic reaction, that is ATP hydrolysis, to this endergonic reaction, which is glutamine synthesis, we have a net negative delta G. It is thermodynamically possible, and the cell can do it. They can actually run this process. And that's the beauty of energy coupling, is to loan energy from ATP hydrolysis into endergonic processes. So the really important message here is that you know that cells need ATP to live, and you should know why, and I just explained that. That is energy coupling. Okay. And you should also know that synthesizing 1 mole of ATP requires energy. So in order to do the synthesis to build the ATP up, you have to have an input of 31.8 kilojoules of energy. So cells need ATP, therefore they have to make ATP. That means they have to have a source of energy to make the ATP. All right? So where does that come from? It comes from chemical reactions. So if a microbe has access to an energy-yielding catabolic reaction, as long as that process has an associated free energy change, or delta G, that is at least equivalent to and preferably greater than that required to make ATP, then it can make enough ATP in order to live. Okay? And that's why doing these calculations and doing this math is handy. It allows us to know if different microbes are able to exist in certain chemical conditions. So it lets us make predictions about their growth and also predictions about the fate of the chemicals that they might be using in the environment. As homework that we will take up in class, I would like you to solve these problems using the methods that I demonstrated on the slide in the previous lecture. So you're asking the question, could a microbe use any of these 3 chemical processes to live? And by 3 processes, I mean the processes shown over on the right. Okay, so here, here, and here. Okay, check to see if the chemical reactions are balanced, and if so, then calculate the delta G for each of those chemical reactions using the energies of formation found in the table shown here on the slide. Please do that for homework. Also as homework, please look at the chemical processes and determine what the energy category would be, or what the metabolic category would be for a microbe that used each of those 3 processes. Would they be chemoorganotrophs? Would they be chemolithotrophs, for example? And do they use oxygen or don't they use oxygen in the reactions shown? I'd like you to use descriptive terminologies and describe those microbes and calculate the delta G's so that you can answer the question, could a microbe use any of these 3 chemical processes to live?